Okay.
Like on number one and number two, I noticed that you had put a number for like the sequence.
Okay, let me find the test here for a moment. Um, okay, hold on. Let me page through and get to it. All right, I'm getting closer. Okay, I think I'm almost there. Okay, are we talking about the Chapter 8 test?
No, the chapter 9 and
9 and
10
10
test.
test. Okay, that's what I was wondering about. Okay, hold on. I'm at Chapter 8 now. Chapter 8, Chapter 8. All right, that's Chapter 8. Okay, here's Chapter 9 and 10 test. And which one are you asking about?
Just about the sequence. Is it like whatever the number is, n plus 1?
Okay, are we talking about question one, two, three? Which one are we talking about?
Number 1.
Number one. Okay, now, um, here's what my question said, and I wondered the reason I'm saying it this way. Sometimes I really dislike PowerPoint. Microsoft products. I totally dislike Microsoft Corporation. Okay, what they do is they come out with a new product and then they don't make it compatible with the older projects. So that's what I'm asking about now is what you can read or you can't read. I've had students say they can't read things on there. So here's what I have for their first question. Write the first 5 terms in the sequence, and the sequence is a sub n is equal to open parentheses negative 2/3 close parentheses raised to the nth power. Is that what you see?
Yes.
Oh, you do. Okay. So yeah, what you're to do then is write the first 5 terms. When n is equal to 1, when n is equal to 2, when n is equal to 3, when n is equal to 4, and when n is equal to 5. Those are the 5 terms that you're to write in that sequence. And I think I left 5 blanks there. Is that right? Okay. Did that answer your question?
Yes.
Okay, okay. See, I was afraid maybe the a sub n didn't show up. And if that was the case, then you would be hard pressed to know what I was talking about. But if you have the a sub n, that's what you do. Right? The first n terms, n equal 1, 2, 3, 4, and 5. Okay? Is that, was that your question then? Or were there others?
That's it.
Okay. All right. Good. Any other questions? Good questions. Okay? Um, and like I said, sometimes PowerPoint, Word, Microsoft products just do a really lousy job of doing. And see, this is a computer that I got from the campus, and I don't know what version of PowerPoint of Word they have on here, but I have had other students in other classes. Oh, here comes Laron. He was here, and now he's coming back. Okay. All right. Laron is trying to connect to audio again. All right. Welcome back, Laron. Okay, let me make sure there's nobody else sitting out there waiting to come in. Nope, don't see them. Okay, we got 4, got half the class here. Hopefully the other half will be showing up. All right, any other questions? Good question. Now, um, we're in chapter 11. Okay, I was trying to find it. Section 11.5, and we're on example 2. And the slide shows example 1 here. That's because there is no example 2. So let me start from the current slide. I guess I'll just do that. Okay. Now we did example 1 last time, so okay. And example 2 we're going to do before we get to planes in space. Okay. So, any other questions before we get started today? Sorry we've had the delay, but that's been a situation with internet. And by the way, my wife was telling me this morning and last night as well, I guess there's a hurricane that is either has already hit the west the Gulf Coast or is about to hit it. Have y'all been following it at all? But anyway, we are supposed to receive tropical storm winds and rains and that kind of stuff. I don't know, I can't remember when she said that was to get here, but it could easily be that we're going to have some pretty rough weather. It doesn't look like it so much now, but that may be one of the reasons that the internet blinked out earlier, is that somewhere in the area they could be having some really rough winds. So if that's the case, stand by for heavy rolls, as they used to say in the Navy, because we could have some other circumstances arising that may in fact influence our reception and that kind of stuff. So anyway, right now I'm trying to adjust my whiteboard so that I can have as much white space as possible here. You probably can't tell I was doing anything, but I was. Okay. Any questions before we go to example 2? Okay, example 2 is the top of page 788. Again, we're in chapter 11, Vectors in the Geometry of Space, and 11.5, Lines and Planes in Space. Example 2 is on page 788, and example 2, you can go to larsoncalculus.com for an interactive version of this type of an example. So here's what we've got. If I can get my pen to show up here. Okay, find a set of parametric equations of the line that passes through the points. So here's the first point. -2, 1, 0. There's a point in space. Here's a second point. That's 1. Oops, here comes Houston. Good deal. All right, the top part of the alphabet is just surged into the lead here. 3 in the top part, 2 in the bottom part, 3 missing in the middle. So hopefully others will be showing up. Welcome, Houston. All right, we're doing example 2. We're on page 788, chapter 11, Vectors in the Geometry of Space. 11.5 is Lines and Planes in Space. We're on page 788, example 2, and this is also found at larsoncalculus.com. You can see an interactive version of this type of an example. So here are 2 points in space, -2, 1, 0, and where is my pen? Well, it's the wrong end of the pen. There we go. 1, 3, 5. Now, I would volunteer to draw this for you. However, my drawing of 3-dimensional space on a 2-dimensional plane leaves a lot to be desired. So let's just go from here. Okay? Now, it says find a set of parametric equations of the line that passes through those 2 points. Okay? Now, one of the first things to do is to identify the vector represented by those 2 points. Okay? And I think they name it V. Okay? So let's us name it V as well. Vector V is the vector, and they named this as point P, and this is point Q. Okay? Not that it really matters any. So we're going to do that, and this vector V is going to be the vector from P to Q. P is the initial point, Q is the terminal point. So I'm going to write this in vector notation, component notation. That would be 1 minus a minus 2. That would be 3. comma, 3 minus a 1, that would be 2, comma, 5 minus 0 would be 5. So there is the vector v, or pq, that goes between the first point p and the second point q. That's the vector. Okay. Now, we now have a vector giving us a direction, and we have 2 points. And it really doesn't matter which one we choose, but this, by the way, 3 to positive 5, this you can represent as the vector ABC, where A, B, and C are your directional now one thing direction numbers, I couldn't remember what they call them, direction numbers, A, B, and C, 3, 2, and 5. Okay, now how do we find the parametric equations? Well, the parametric equations would be x is equal to, pick a point, either point, doesn't matter which one. I think they probably use the first point, negative 2 plus 3t. Okay, y is equal to 1 plus 2t, and z is equal to 0, you don't have to write that down, 5t. Okay, there is a set of parametric equations. X equal negative 2 plus 3t, y is equal to 1 plus 2t, and z is equal to 5t. Okay, now you didn't have to use that point. You could have used the other point. It would have given you the same quantities, but it just would have looked differently. Okay, and that's it. That's really all you have to do here. Okay, now they picked a few points for t. For instance, t is equal to 0, and if you pick t is equal to 0, you get the point negative 2, 1, 0. Yeah, there it is. Okay, if you pick the point t equal 1, negative 2 plus 3 would be a plus 1, 1 plus 6, 1 plus 2 would be 3, and 5 times 1 would be 5. So you pick the value t is equal to 1, you get the second point. And pick any other t, and you'll have another point that's in the direction of v, or PQ, and is on that line. Okay, so that's what we've got there. All right, any questions on that? Now, let's go back to our PowerPoint, and we'll go back to the slideshow. And we finished example 1 and 2 now. We're ready to move to planes in space. Now, these aren't airplanes in space. These are planes, flat, two-dimensional, geometric constructs that happen in space. Okay, for instance, the wall back here behind me, that's a plane in the space of this room. That door back there, that's a plane in this room. Okay, the ceiling is a plane in the room. Any two-dimensional structure in the this space or any space would be a plane in space. Okay, now consider the plane containing the point P, x1, y1, z1. We just had 2 points that defined a line. This point here is in a plane. Okay, lines, by the way, are in planes as well. Okay, now it has a non-zero normal vector. Okay, now what do we mean by that? A plane, remember, is a flat sheet. Okay, that's it, two-dimensional sheet. A non-zero normal vector means the vector that's normal to, perpendicular to that plane, is not the zero vector. Okay, so if this is your plane here, there is a vector coming out of that plane, normal to the plane, and it's not the zero vector. Okay, now here is an illustration of that. Here, the purple plane here is a plane. The normal vector coming out of there, perpendicular to the plane, is a non-zero vector. Okay. Now, that plane consists of all the points Q, X, Y, Z, for which the vector, it looks like they've left something out here, and I do believe they have. That is a really weird looking form here. Okay. I have taught this before and I've never noticed this. I don't know what the deal is. Okay. For which the vector, and that's supposed to be PQ. So let me fill that in here. The vector PQ is orthogonal to, okay, so this thing should have been right there, okay, and then instead of this, it should be orthogonal to N, okay. Now, your N is your perpendicular vector, your orthogonal vector, normal vector, to that plane. You have a point in the plane, P, X1, Y1, Z1, and then that plane consists of all the points Q, okay, that are anywhere in this plane, that point Q. P is a fixed point, Q is a variable point, anywhere in the plane, and this vector here, PQ, non-zero vector, it has to be perpendicular to the vector N, okay? Now, using the dot product, remember the dot product of two perpendicular vectors is always 0. So N, which by the way was ABC, okay, if this is looking similar to what we had before with a line, the ABC are your direction numbers. Now these are your direction numbers of a vector that is perpendicular or normal to a plane. Okay, now using the dot product, you can write the following: N dot PQ. Now remember, PQ is basically X minus X1, comma Y minus Y1, comma Z minus Z1. Okay, N is the ABC here. So you dot those two together, you get A times X minus X1 plus B times Y minus Y1 plus C times Z minus Z1. That's equal to 0. That third equation, this thing right here, of that plane is said to be in standard form. Okay, now get it. It is an equation. There is an equal sign. Usually we have the equal 0 over here. It doesn't have to be. If you multiply A, which is a number, times the minus X1, that gives you a number. B times minus Y1, that would give you a number. C times minus Z1, that would be a number. And if you added those to this side, you would have AX plus BY plus CZ is equal to some number here. That's not quite in standard form, but it's close enough. That's also. So the normal vector N is orthogonal to every vector PQ in that plane. Okay? Every one of them. Okay. So here's theorem 1112, the standard equation for a plane in space. A plane consisting of the point X1, Y1, Z1, just a point in the plane and having a normal vector in a comma b comma c, okay, vector components, can be expressed by the standard form of the equation of a plane, a times x minus x1, those are the x1, y1, 2, plus b times y minus y1 plus c times z minus z1 is equal to 0. Now, here's what I was saying before. You can regroup those terms to obtain the general form of an equation of a plane in space. Now that one would be, remember I said a times x1 or minus x1 is just a number, b times minus y1 is just a number, c times minus z1 is a number, and if you add those together, those numbers, ax1 or negative ax1 minus bxy1 minus cz1, add them together, make that a d, okay, set that equal to 0. That's the general form for an equation in space. The standard equation has the x1s, y1, and z1s in it, okay, identifying that initial point. You don't have to know the initial point. This form has that. Given the general form of an equation in a plane, it is easy to find the normal vector to the plane. That's your coefficients of x, y, and z. That's your normal vector. Just pick those I'm not able to think of my word there. Coefficients of your x, your y, and the z, make those your normal vector. Okay? So it's just use the coefficients of your x, y, and z, write it down. Now, why in the world that advanced, I don't know, but it did. And we're ready for it too. We're doing example 3 now. Finding the equation of a plane in 3 space. So it says here, find the general equation, not the standard, but the general equation of the plane containing these 3 points. Okay? Now, here's point 1, point 2, point 3. These are points with parentheses around them. These are coordinates of a point. Okay? How would we find the general equation? Well, let's find the vector between these 2 points. That's got to be in the plane. So that would be, and it doesn't really matter what you would do, let's call that vector v maybe. Okay? And that would be 1 minus 2 would be a minus 1, comma, 4 minus 1 would be a 3, comma, 1 minus 1 would be a 0. Okay? This vector is in that plane. Okay? You could also do the same thing and call it vector u. Now that's not a unit vector, it's just a vector u. And that would be, let's just take this point. Negative 2 minus 2 would be a negative 4. 0 minus 1 would be a minus 1. And 4 minus 1 would be a 3. There's another vector in that plane. Okay? Now, 2 vectors in the plane, any old vectors in the plane, their cross product has got to be perpendicular to both of those. That's going to give us the normal vector. Okay? So what we'll do then is cross these 2. So v cross u, cross u, it doesn't matter which order you do them, okay, it's fine, will be, and remember we set up our determinant, I, j, k, and then I'm going to repeat the I and the j. Repeat the first 2 columns. Okay? Now that's not legitimately a determinant here, but I'm going to draw it as if. And then let's write v here, minus 1, 3, 0, minus 1, 3. Just repeat the first 2 entries. And this will be minus 4, minus 1, 3, minus 4, minus 1. Now let's do your down diagonals. This will be 9i 0j plus k. Okay, now I'm going to erase, just because it gets pretty crowded looking if you leave all those lines in there. Okay, now let's do the up diagonals. That would have been a minus 12k, except going up, you negate it, so that would be plus 12k. The next one is your good old 0. Okay, and the next one to that would be a plus 3j, because that would have been a minus 3, but you're going up, you negate it, so that would be plus 3j. Well, what's that cross product between these? 9i, I've got to sneeze, sorry about that. Sorry, came out of the blue there. Oh, excuse me. Sorry. Okay. 9i plus 3j plus 13k. That is your normal vector to this plane, the plane that contains those 3 points. Okay? That means this is your 9, 3, 13. That's your A, B, and C. Okay? Now, the general equation containing those points would be, remember, 9x, well, actually I'm going to write this as 9 times x minus n. It doesn't matter which one you choose. Why don't we choose this point here, 2, 1, 1. So that'd be minus 2 plus 3 times y minus 1 plus 13, that's your c, times z minus 1. And that's equal to 0. Now that's your standard form. Okay, so let's multiply through, and this gives you 9x minus 18 plus 3y minus 3 plus 13z minus 13 is equal to 0. Add these constants together here, and you get 9x plus 3y. I left off my z here, didn't I? Okay, plus 13z. Okay, add these 3 together. 18, so minus 18 minus 3, that's minus 21. Minus 13 is minus 34, I believe it is. Minus 34 is equal to 0. That's your general equation for the plane containing those 3 points. Okay, now is that unique? No, it isn't. You could have chosen to arrive at this another way. Let's see if this, how close it is to the one that they have. Okay, this is example 3. 9x plus 3y plus 13z minus 34 equals 0. Yes, we have the same general form that they had. All right. Now, let's see if they did it the same way we did. I'm going to erase my ink. Any questions on this before we get going? Any? Okay. Now, to apply the theorem 1112, you need a point in the plane and a vector that is normal to the plane. Well, we have 3 points in the plane. Any one of those would do. But what we need is a vector that's normal or perpendicular or orthogonal to that plane. They usually use the word normal there. Okay, now how do we get that? We know all three of these points are in the plane, so the vectors connecting these 3 points, okay, are in the plane, and pick any two of those vectors, cross them with each other, and you get a vector that's perpendicular to the plane. And that will give you your ABC, your direction numbers. So there are 3 choices for the point, but no normal vector is given. Okay? So any one of those 3 points will work, but you need a normal vector. So what we do to obtain a normal vector, use the cross product of vectors u and v, extending from the point 2, 1, 1 to the points 1, 4, 1, and the other point negative 2, 0, 4. Okay, so here's one of those points, 2, 1, 1. The one going to 1, 4, 1 is this vector. The one going to negative 2, 0, 4 is going that way. Okay, so what we do is find out the components of those 2 vectors, which is a real easy thing to do. 1 minus a 2 is a minus 1. 4 minus 1 is a 3. And 1 minus 1 is 0. I think we use the same one. I think I named that V, they named it U. Doesn't matter. Okay. V, the other one, would be negative 2 minus 2, which would be a minus 4. 0 minus 1 would be a minus 1. And 4 minus 1 would be a 3. So yeah, we use the same 2 vectors, we just named them differently. I named the first one V and the second one U. They named the first one U and the second one V. It doesn't matter. What do we do with them? We cross them. Okay, do a cross product, and that guarantees to give you a vector normal to that plane. So that cross product again is ijk, and then choose either one of those, negative 1, 3, 0, negative 4, negative 1, 3. Okay, now they don't show the nitty-gritty of it, they just come out with the answer, 9i plus 3j plus 13k. Perfectly fine. That's your A, B, and C, your direction numbers for the normal vector to those 3, the plane formed by those 3 points. Okay, that's your ABC, direction numbers. Using those direction numbers for n and the point, and it didn't matter which point you used, they chose the 2, 1, 1, same that we did, I think. You can determine the equation of the plane in standard form by a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. That's the standard form for that plane that we're talking about. Now, my head is closing in on me. Hold on just a minute. Let me do something to sort of loosen it up. Sorry about that. Okay, that's in standard form. They didn't ask for standard form, they asked for general form. What's the general form? Distribute the A times what's in the parentheses, B times that parentheses, C times that parentheses, see what you get. A was 9, so 9 times x minus 2, since we chose that be the point we're using, plus 3 times y minus 1, since that's the point we're using, plus 13 times z minus 1, that's the point we're using. Okay, multiply those together, you get 9x minus 18 plus 3y minus 3 plus 13z minus 13 equals 0. Combine the 3 constants together and you get 9x plus 3y plus 13z minus 34, negative 18, negative 3, negative 13. These two would add to be negative 31, and 3 more negative would be negative 34, equals 0. There's your general form. That's the standard form. Here's the general form. Okay? Any questions? Now, two distinct planes in 3 space are going to have these characteristics. Either they're going to be parallel to each other, or they're going to intersect in a line. Two distinct planes in 3 space are either going to be parallel, or they're going to intersect in a line. It's a lot like two lines in a plane, in a given plane, are either going to be parallel or they're going to intersect at a given point. Same thing here, except you step it up a notch. Two planes in 3 space are either parallel to each other, never crossing, or they cross in a line. Okay, so for two planes that intersect, you can determine the angle that's between 0 and pi halves between them from the angle between their normal vectors. Okay, so this is what we're showing here. If this is plane number 1, okay, there's its normal vector. Here's the blue plane, here is plane number 2, that's its normal vector. The angle in between is the angle between those two vectors. That's also the angle between the two planes. Okay, now specifically, if the vectors n1 and n2 are normal to the two intersecting planes, then the angle theta between those normal vectors is equal to the angle between the two planes, and that is cosine theta is equal to the absolute value of the dot product between the two vectors divided by the product of their magnitudes. Okay, now let's think on that for just a moment. Because we're doing absolute value of the dot products could be positive or negative, we're doing absolute value, that's always going to be positive. The magnitude of n1 is always positive, the magnitude of n2 is always positive, so everything here is positive. Well, cosine of this angle is positive, that means the angle is in the first quadrant, and that's why we said earlier that it's in between 0 and pi halves. The angle has to be in the first quadrant. Okay. Consequently, two planes with normal vectors n1 and n2 are perpendicular when this dot product is 0, okay, and they're parallel when n is a scalar multiple, n1 is a scalar multiple of n2, okay. That's not the only two possibilities, but it's two that we want to focus on. Perpendicular when the product is 0, parallel when n1 is just a scalar multiple of n2. Okay, now they're skipping example 4. So let's go back one slide and go to our whiteboard. Okay, all right, to clear this. Okay, now excuse me just a minute. All right, for some reason today I have just been thirsty all day long, which then after a while means I have to go to the bathroom all day long. So hopefully we'll make it through this class without it. We go until 1:55, so hopefully I can make it the next 45 to 50 minutes or so without, but let's see. So here's example 4, top of page 790. Okay. Find the angle between the two planes. So here's the first plane, x, Whoa, here comes Jemanuel. Good deal. Well, I'm trying to let him in. Hold on just a minute. Let me get him marked here. Okay, Jemanuel. All right, now we're evened it out again. We got the top three in the alphabet, the bottom three in the alphabet. We're missing the two in the middle. So hopefully they will be coming in fairly soon. Okay. Now, Jemanuel, we're on in Chapter 11, Vectors in the Geometry of Space, in Section 11.5, Lines and Planes in Space, and we're on Example 4, the top of page 790. We're finding the line of intersection of two planes. So here's the first plane. X, if I could find my pen here. There it is. Okay, x minus 2y plus z is equal to 0. Now, time out for just a moment here. Okay? Notice what's not here. We don't have that constant d. What does that mean for you? That means this plane that we're talking about, this plane here, has to go through the origin. Because when x equals 0, y is equals 0, z is equals 0, you get 0. So this plane has to go through the origin. If you had a constant there, non-zero, okay, then the odds are it wouldn't have gone through the origin, but this one did. Now here's the second plane. If I can get my pen to show, there it is 2x plus 3y minus 2z, and that's equal to 0. Well, guess what that means? This plane also goes through the origin, because 0, 0, 0 makes that a true statement. Okay? So, we've got two planes that both of them cross at the origin. Now, we know they cross at more than one point. They cross in a line. So that's what we got to figure out. The line, that's what it's asking for. No, it's not. It's asking for the angle between the two planes. And then it says, then find the parametric equations of their line of intersection. So yes, we are finding that also. And remember, you define a line with parametric equations. Okay. Now, let's start with the what they're asking for, the angle. Okay, I couldn't think of the word. Okay, now, remember, and Jemanuel, this is before you came in here, we use the direction numbers at what the direction numbers are the coefficients of these equations here. So let's call this line 1. So n1, the normal vector for this plane, is going to be 1 minus 2, 1. The normal vector for this plane, we'll call it n2, is 2, 3, negative 2. Okay, we know the normal vectors for those two planes. They are the coefficients of the variables. Okay, that's exactly what they are. Now, given that, what we just did before told us that the cosine of the angle theta between these two is going to be the magnitude of m1 dot n2 divided by the this is the absolute value. I said magnitude, but same type principle, but it's absolute value. The magnitude of N1 times the magnitude of N2. Okay. Now, let's do the dot product between those two. Dot product, remember, is the product of the corresponding terms. 1 times 2, that would be 2. Negative 2 times 3 would be minus 6. And 1 times negative 2 would be negative 2. Okay, we're going to do the absolute value of that divided by, and then the magnitude of this one is going to be the square root of 1 plus 4 plus 1. That's the square root of 6. Okay? Times the magnitude of this one, which is the square root of 4 plus 9 plus 4. Okay? So, this is going to be 6. Absolute value of negative 6 is 6 divided by the square root of 6 times, and this will be the square root of 8 plus 9 is 17. Okay, now that would be 6 over the square root of no, I thought my phone was buzzing. It's not. It's 42,102, I believe it is. I'm doing it in my head fairly quickly. Now let's see if that's what they got. Like I said, I'm doing it fairly quickly. Yeah, 6 over square root of 102. So I'm going to pull out my handy dandy phone, which serves as my calculator here, and alright, get my calculator mode going here. Turn it sideways because I need square roots in here. So we have 6 divided by the square root of 102. So I have to enter the 102 first, then do the square root of that, and then press equal. Okay, now what I've got there is approximately 0.594. 0.594. Now I've rounded. Okay, and that's the cosine of this angle in between. Okay, so how do you get the angle in between? You take the inverse cosine of 0.594. So I don't know if y'all are using telephones or actual calculators, but with a telephone you go to the second module, and that's the second right there. Okay, and that gives you inverse cosine next to the last row. So I'm going to do, now I need to be in radian mode. I happen to be, I'm pretty sure, in degree mode, so I'm going to make it to radian mode. Then I'm going to do an inverse cosine, and when I do the inverse cosine, I get 0.93 blah 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 blah. So this is approximately equal to, where in the world, oh there it is. Okay, theta is approximately equal to 0.935. I'm going to just round it there. That would be radians. Okay, and they got, whoa, okay, I'm sorry, my word, they went to degrees. I don't know why. Usually you say in radians. Okay, sorry about that. Let's go back to let's see, will this work? Nope, I just botched it. Okay. All right. I had 0.9594, and in degree mode, then do your second and do the inverse cosine, and they get approximately, where is, there it is, approximately 53.6 degrees, which is pretty close to 1 radian. Okay, they did 0.55. Well, I got 0.56, but anyway, I had rounded earlier. Okay, now that's the first part. Find the angle between the two planes, and we said about 50, I would just say about 54 degrees. Okay, 53.6 degrees. Okay, now then find the parametric equations of their line of intersection. Okay, and they're asking for they show the figure here. So we need the parametric equation of that line of intersection. Okay, now how are we going to define that? If we were to do a the line of intersection means that these two lines right here have to be equal to each other. Okay, so what we do here is set these equal to each other. Okay, so what we have here, if I could find my pen here, there it is. Okay, let's see if we can do it down here. X minus 2y plus z has to equal 2x plus 3y minus 2z. Okay, and I would subtract this from that. So this would give us x, 2x minus x is x, 3y minus 2y minus a minus 2y would be plus 5y, and then minus 2z minus z would be minus 3z. That would equal 0. Well, of course, the line of intersection has to contain the origin, and that contains the origin. Okay, now this gives you your direction numbers: 1, 5, -3. Okay, and then just use those. It says find the parametric equations for that line of intersection. So basically that would be, if I could get my pen to show up here, there it is. Okay, you would have x, and use either one of these 2 points. Okay, let's see, a point that's on either one. Well, why not 0? We know 0, 0, 0 is on this thing, so we'd have 1 times x. Okay, so x minus 0. I want my pen to show, there it is. Okay, it's writing all over the place. Plus 5y minus 3z. Okay, well, I've just rewritten that. Sorry about that. Basically, that's your parametric equation right there. Okay, well, let's see, we need a t's in there, so it'd be okay, start this over again. It would be x minus 0, that's the first point, So x plus t, and let's see, does it say just parametric equation? That's equal to um, sort of going blank in my head here. I think it's equal to 0, okay? Y minus 2t is equal to 0, and z minus 3t is equal to 0. Okay, let me make sure I've written that correctly. Okay. You can find the line of intersection of the two planes by simultaneously solving the two linear equations representing the planes. One way to do this is multiply the first equation by minus 2, and that was that one. Okay, no, I haven't done it right. Sorry about that. Let me clear this again. Let me just make sure. Nah, okay. All right, let's start over on that one. Sorry about that. Let's go back to where we were. I had written down these two equations. The first one was x minus 2y plus z is equal to 0. Okay. And the second one was 2x plus 3y minus 2z, that was also equal to 0. Okay, those were the two lines we had. Now I set them equal to each other, which sort of made sense, but it doesn't quite get us what we want to do. Okay, we want to solve these simultaneously. Now it's not completely obviously why we're doing that, okay, but let's do it. So multiply the top equation by a negative 2 and add it to the next equation. So this will be minus 2x plus 4y minus 2z is equal to 0. And the second equation is 2x plus 3y minus 2z is equal to 0. And when you add these two together, the x's go out and you get 7y minus 4z is equal to 0. Okay. Now, you could write that as 7y is equal to 4z by adding 4z to both sides, then dividing by 7, and you get y is equal to 4/7 z. Now, z is just a number, okay? I mean a variable, okay? Now, that means you could rewrite this as y is equal to 4/7 t. Let z equal your parameter t. okay, then y is equal to 4/7 t. Now take that and plug it back into any one of the equations here, okay, and that would give you x minus 2 times y. Well, y is 4/7 t, so that would be minus 8/7 t, because y is 4/7 t, okay, plus, and your z was t, plus t is equal to 0. Well, add those two together and you get x. This is minus 8/7 t. This is plus 7/7 t. That would be minus 1/7 t is equal to 0, and that gives you x is equal to 1/7 t. Okay. Now, let's just look at a moment. When t is equal to 0, x equals 0, y is equal to 0, z is equal to 0. We know the origin had to be on that line. So sure enough, we've got that right, and that are your parametric equations. X equal, now, they do one other thing. You could have left it the way we did, or multiply all three of these equations by 7. That would then give us x equal t, y is equal to 4t, and z is equal to, you multiply every one by 7, z is equal to 7t. So there's another set of parametric equations. X equal t, y is equal to 4t, z is equal to 7t. Perfectly works. Plug in as t equals 0, you get the origin, which you knew had to be on that. Okay. Now, those are your direction numbers for the line of intersection, 1, 4, 7. Or it could have been 1/7, 4/7, and 1. That would have worked too. But those are your direction numbers for the line of intersection. Now, it says then find the parametric equation for the line of intersection. There it is. Okay. Now it says note that the direction numbers in example 4 can be obtained from the cross product of the two normal vectors. Now we didn't do that. I was tempted to do it, but I wasn't sure they were going to introduce it. We did. So what we could have done is cross the two normal vectors. Okay. Now the first one was yeah, okay. If we had done that instead, which I think would have been an easier process to do, let's do, if I could, oh, this is so aggravating. Okay. Your normal vector here, and why it's writing I don't know, would be n1, which we had before, was this normal vector here, 1, -2, 1. Your n2 here was this vector here, +2, 3, -2. Okay, those are your direction numbers for those vectors. Okay, now do a cross product, n1 cross n2. Okay, remember how to do the cross product. Set up your, sort of like a determinant, I, j, k, I, j. 1, -2, 1, 1, -2. And 2, 3, -2, 2, 3. Okay, now do your magic here. That would be 4i, write it somewhere here, 4i plus 2j plus 3k Alright, those are your down diagonals. Let's see if I can get them to erase. Yes, I think I can. Yuck. Okay, I lost my J and I lost part of my K. Okay, now let's do our up diagonals, and that's going to be plus 4k this one will be minus 3i, and this one would be plus 2j. Okay, add those together, you get I plus 4j plus 7k. Okay, now that is a vector that's perpendicular to both n1 and n2. So therefore that must be along the line. The line of intersection has to be in that same direction. Now all you have to do now is set notice your x equal t, y is equal to 4t, z is equal to 7t. That will give you that vector. Okay, now to me that would have been the easier way to do it than simultaneously solving, but I wasn't sure if they were going to do that. Okay, so what it means is the line of intersection of two planes is parallel to the cross product of their normal vectors, of course. Okay, now let me get my calculator out of the way here and my book out of the way here because it's hot and heavy. Okay, and that was example 4. Any questions? All right, where we're going to go is back to 11.5 and go back to the slideshow, and we're going to now move to sketching planes in space. Not my favorite activity of all time because they're really hard to sketch. If a plane in space intersects one of the coordinate planes, okay, then the line of intersection is called the trace of the given plane in that coordinate plane. So to sketch a plane in space, it's helpful to find its points of intersection with the coordinate axes and those traces of the coordinate planes. Okay, a lot of blah blah blah. Actually, it turns out being a little easier than what it sounds like, or I hope you'll find that the case. Okay, for example, let's consider the plane 3x plus 2y plus 4z is equal to 12. Now that's an equation of a plane. That's not the standard equation of a plane. It's not the general equation of the plane, but you could get either one of them. Okay, well, you could get the general. Just subtract 12 from both sides and you got the general equation. Okay. Now you can find the xy trace by setting z is equal to 0, because in the xy plane z is always 0. So set z equal to 0 here and you get 3x plus 2y is equal to 12. Okay, pretty straightforward, right? That's the xy trace of this plane on the xy axis. Okay, in the xy plane, not axis, plane. The line intersects the x-axis at where? Okay. The x-axis is where y is equal to 0. So put that equal to 0 and you have x equal 4. Okay. It intersects the y-axis. Okay. The y-axis is where x is equal to 0, and that would be 6. So 4, 0, 0 and 0, 6, 0 would be the 2 points on in the xy plane that line intersects the xy plane. Okay, 2 points, and the line between those 2 points will be the intersection. Now, you could do the same thing. Set x equals 0 and find for the YZ plane. Okay, when x equals 0, then you have 2x plus 4y is equal to 12. So when z is equal to 0, you'd have 0, 6, 0, which is the same one we had here. And then when y is equal to 0, you would have 0, 0, 3. Okay, so that would be another point. And then when you do the other one, you'll find you get this point and the previous one. So all right, so here's what we got. In this figure, that process is continued by finding the YZ trace and the XZ trace, and then shading the triangular region lying in the first octant. Okay, first octant, we don't number all the octants, but the first octant is where x is positive, y is positive, and z is positive. Okay, so here's that first one we got, 4, 0, 0 and 0, 6, 0. Then when we did the same thing for the second one, we got, in addition to 0, 6, 0, we got 0, 0, 3, and then all you do is draw a line from that one to this one, and here is the sketch of that plane in the first octant. It goes into the octant behind, to the left, down, it goes everywhere, but there is the that triangular area is in the plane from there. So yeah, I think we've beat that to death. All right. If an equation of a plane has a missing variable, such as 2x plus z is equal to 1, then the plane must be parallel to the axis represented by the missing variable, the y-axis. Okay, and if this is your description of that, this plane is parallel to the y-axis. Okay, it doesn't intersect the y-axis anywhere, it's parallel to it. Okay, that's if you're missing a variable in the equation of a plane. Okay, now you could have done the same thing we did before. Excuse me. All right. The set, say z equal 0. So in other words, you're going to be in the xy plane. This would be the line in the xy plane. 2x is equal to 1. So x equal 1/2. So there is your point 1/2, 0, 0. Same thing here, set z equal to 0. I'm sorry. X equals 0, and you got z is equal to 1. 0, 0, 1 would be here. Now, this then defines that plane. You don't have a y here, so you don't have a y intersecting point here. So this will then be parallel to that y-axis. Okay. Now, if two variables are missing from an equation of a plane, such as ax plus d is equal to 0, then it is parallel to the coordinate plane represented by the missing variables. So if all you got is x equal minus d over a right there. Go out the x-axis minus d over a. Now, I don't like the way they've drawn this, okay? Because you think of the d being positive and the a being positive. It's obviously not, okay? Because this is in the positive x-axis. So either d or a is negative. I don't know which, okay? They really should have put this back here, I think, but they didn't, okay? Now, if you set x equals 0 here, let's see, that's not what I want to do. Oh, I'm sorry. Yeah, this would be the plane by plus d is equal to 0. And again, they've got a positive value here given as negative d over b. So I don't know why they did it that way, but they're doing it. And then this one, this would be parallel to the xy plane. And again, they did this as being a positive value, but with a minus in front of it. So don't know why they did it that way, but they did. Okay. Now, where were we? All right, we're on page 792. Okay. Let's talk about the distances between points, between planes, and between lines. Okay. Now, consider two types of problems that involve distance in space. Finding a distance between a point and a plane, and also find the distance between a point and a line. Okay. So, what we have is a point somewhere, and you want the distance between that point and a plane, and that point can't be in the plane, okay? Or find the distance between a point and a line where that point can't be on the line. The distance d between a point Q and a plane is the length of the shortest line segment connecting Q to the plane. Okay. So here we have a point P in the plane. Here we have a point Q not in the plane. Okay, we want the distance between Q and that plane. It's certainly not this distance here. Now, I guess occasionally it could be, but it's not. Okay, it's the distance here, the shortest distance between Q and that plane. That's the distance you're talking about. Now, they show this as the projection of the normal vector for that plane, okay? And if we know the plane, we know the normal vector to it, okay? So the projection of that point PQ, that line PQ, onto that normal vector, okay? Now we did that a little bit earlier, and we will do it again now. That's the absolute, or the magnitude of the projection of PQ, that's this line here, onto the normal vector N. Okay, that's the distance between a point and a plane. For any point P in the plane, you can find that distance by projecting the vector PQ onto the normal vector N. And the length of that projection is your desired distance. So here's your theorem, 1113. The distance between a point and a plane, the distance between a plane and some point Q not in the plane is, that distance, capital D, is the magnitude of the projection of PQ onto N. Okay? So that, going back to what we did before, that's the dot product of PQ times N divided by the magnitude of N. Okay? Where P is a point in the plane, N is normal to the plane. Okay. Now, to find a point in the plane, okay, here's a point in the plane, ax plus by plus cz plus d is equal to 0. That is an equation of a plane, okay? Where a is not equal to 0, to find the point in that plane where a is not equal to 0, then let y and z both be equal to 0, as long as a is not 0. Then from the equation ax plus d is equal to 0, you can conclude that the point minus d over a, that's what you get when you solve this for x, comma 0, because that's your y and your z, lies in the plane. Okay? Now, let me just make sure. Okay. Now, let's do example 5. This will probably take some going back and forth because this was, so here's example 5, bottom half of page 792. Find the distance between this point Q, right here, 1, 5, negative 4, and the plane given by 3x minus y plus 2z is equal to 6. Okay? Now, we know the normal vector to this plane would be, let's just call that n, is equal to your direction numbers here, 3, minus 1, 2. That's the normal vector to that. Okay. Now, here's something I like to do first. Let's make sure this point Q is not in that plane. Okay? So we're going to plug in 3 times 1 is 3, minus 5, that would be a minus 2, minus 8, that would be a minus 10, minus 10 is not equal to 6. Okay, good. We know this point Q is not in that plane. Okay? Cannot be in the plane. Okay. Now, what is a point that is in that plane? Okay? It really doesn't matter which you choose, but one point that's in this plane would have to be 2, 0, 0. That would be in the plane. So the point, I'm going to call it P, is equal to 2, 0, 0. That point is in this plane, okay, because 3 times 2 is 6, minus 0 plus 0 is 6. Okay, that point P is on that plane. This point Q is not. Okay, so what are we going to do? Okay, if you recall, go back here, and the distance between that point Q, not in the plane that we already verified, is the projection of that. That's PQ dotted with n divided by the magnitude of n. Okay, the absolute value of PQ dotted with n times divided by the magnitude of n. Okay, so let's do that. Okay, let's come up with the vector PQ. Okay, P is the initial point, Q is the terminal point. So that would be 1 minus 2, that would be a minus 1, 5 minus 0, 5, and negative 4 minus 0, negative 4. Okay, there's the vector PQ. Alright, so what are we going to do? The distance D is the absolute value of n dotted with PQ. Now, it doesn't matter which one you do. I can't remember if that's how they phrase it or not. Divided by the magnitude of n. Okay, so n dot PQ, there's n, there's PQ. The dot product would be -3, -5, -8. Okay, absolute value of that would be minus positive 16. Okay, divided by the magnitude of n would be 9 plus 1 plus 4. So this would be 16 divided by square root of 14. Okay, now I don't know if you like that or not. If you don't want to leave it like that, you could say 16 root 14 over 14. I see no advantage of that. Let's see what the book does. Well, I can't see what the book did. Yeah, 16 divided by root 14. That's where they left it. So let me get my calculator and see what they got that to be. Alright, I got to turn it sideways because we got square roots involved. So it'd be 16 divided by root 14. About 4.28 approximately. Okay, let's see what they got. 4.28, that's what they got also. Alright, how are we doing? Whoops, we've just run out of time. Okay, now let me clear my screen here. Okay, set my calculator aside, and we've just done example 5. Let's just quickly see how they did it. Sorry, I forgot this is one that you can see how they do it. Okay, you know that n is equal to 3 minus 1, 2. That's the normal vector. Okay, normal to the plane. Okay, to find the point in the plane, let yz equal 0, and then x is equal to 2. So there's a point in the plane 2, 0, 0. Okay, now here's the point not in the plane. They didn't show you, but plug these in, find out that's not equal to 6. Always do that. Okay, then you can do the point PQ to be 1 minus 2 from here, 5 minus 0, negative 4 minus 0. So that's going to be minus 1, 5, minus 4. Okay. Yeah, okay, I got lost where we were there. Okay, then using the distance formula given in 1113, the dot product between PQ and N divided by magnitude of N. So that was the dot product of this vector PQ, it didn't matter which one you did, dotted with N, that was this one, divided by the magnitude of N, which is that, and that gave you minus 3, minus 5, minus 8, divided by square root of 14, and that's 16 over root 14, which is approximately 4.28. Okay, stop there. We will pick up from there next time. So we did example 5. Okay, we're going to be starting bottom of page 792 from the theorem, blah, blah, blah. That's where we're starting next time. And we just have 2 more examples after that. Any questions? Okay, good deal. Okay, folks, I hope you know what Tuesday is. Election day. I hope you're registered to vote. Okay, I sort of hope you've already voted. We have. My wife and I went down in September and voted. Okay, but if you haven't voted yet, please, folks, vote. If you're registered to vote, please please vote. It's an incredibly important election. Okay, now some of you may not be able to vote, but that's okay. But those who can, please vote. Okay. Now, that's going to be on Tuesday. It won't interfere with this class any, but it could be, if you have a Tuesday, Thursday class, it may be that it's going to be hard to get internet because everybody in the world is going to be on the internet trying to follow the election. So stand by for that. That may be a possibility. All right, any questions? Good deal. I'll stop the sharing now, and unless you have some further question, I'm going to end the recording now. Take care, folks. I'll see the three of you, no, two of the three of you tomorrow, and hopefully we'll pick up James as well. So take care, be safe, see you tomorrow. And Jermanuel, you be safe. Okay, we'll see you Monday. Bye-bye.